Okay. All right, circuits. So what you're going to find as we go through this presentation together is that there are places where I circled this in preparation, but they're coming in point by point, so there's going to be weird, random circles and underlines until the words actually appear. And if that bothers you, I'm sorry. There's probably a way I could have made them come in on transitions, but I didn't. So, all right. So the first question we're going to deal with is this: what carries charge? What carries charge? And this is an incredibly important question, not just with regards to what we're doing, but really even more fundamentally than that. How does energy transfer, and how can we utilize that to actually fuel things that we care about, right? Like our televisions and our blenders, right? Those are probably the two most important things in my life, to make milkshakes and to watch Dodger games, right? I mean, it's like, yeah. Those, I'm just kidding. Those aren't the two most important things in my life. They're just what came to me. So what carries charge? What we're going to do is we're going to restrict this to a conversation about electricity, and specifically about a conversation about organized electricity, where we're actually controlling the movement of charge. We can have a completely different discussion about just the full movement of electricity. It'd be fun, but it's a little bit less than, or a little bit more chaotic than what we need to do. And so the first way we'll discuss is what carries charge is with this. When a charge flows through the wires of a circuit, so the wires within a circuit are carrying charge. What's happening is there's a current, there's a movement of materials through the wires. And there's an analogy I want to talk to you about. It's not a perfect analogy, just like there really are no perfect analogies. But the movement of charge through a wire is pretty similar to the movement of water through a hose. Okay? Have any of you never in your life used a garden hose? Okay, so we're on the same page. All right, so you turn the nozzle, right, or the valve, and that opens it up, opens the valve and allows water to flow in. And then water's going to flow through that hose until you close the valve and stop allowing water to move through. But it's basically, ideally it's a one-way flow. And that's similar to how we design wires, to where we have a one-way flow. Okay? And it's actually a movement of materials. Just like the water's moving through a hose, that's a movement of water molecules. And there's actually something moving through wire, bless you, as you have current moving through the wires. It's not a perfect analogy, but it is a good one. And so what's actually moving through a wire, that's the equivalent of water moving through the garden hose, are electrons. Electrons are moving through the wires. They're flowing through the wires, and as they do, they are carrying charge with them. Okay? Electrons bear a negative charge. And so as the electrons move through the wire, they are carrying negative charge through the wire. And so that's what's going on. And again, think about it like water moving through a hose. Now, electrons are teeny, teeny, tiny. And here's where it's not a perfect analogy. Do two negatively charged particles like each other? Think about, any of you ever taken a magnet and tried to put the south poles against each other? And they repel each other? Right? And the reason for that is partially, I mean, that's magnetism, but magnetism is created partially by the movement of electricity. But you get the same thing if you try to force two negatively charged particles together. They don't like each other. They do not interact well. Whereas water molecules absolutely love each other, right? Water molecules can't get enough of each other, and that tends to govern most of the way water behaves. And so it's not a perfect analogy, but understanding that these electrons are negatively charged and therefore repel each other does actually facilitate some of the discrepancies for why things don't match up exactly. Okay, so keep that in mind. All right. Now, just like we want to know the amount of water moving through a hose, right? I guess you really only care about it if, one, you know the amount of water you want, right? Like you want to fill up a bucket, and your bucket is 5 gallons. And you care about how long you're going to have to sit at that bucket. But for most of us, if you don't actually pay the water bill, you just put the hose in the bucket, turn it on, go and do something else, and come back, and you don't mind that it overflowed your bucket a little bit, right? Because you're not worried about it. You know what I'm saying? But for other people, you care about the current, and we certainly care about the current moving through a wire. Because when you're talking about moving charge, that's how energy flows. And when you're talking about moving energy, you're talking about something that is potentially very dangerous. Although moving water is also potentially very dangerous, but not the amount moving through a hose. But the amount of electricity moving through a wire in your house is very potentially dangerous. All right. So the main way we do this is this. Basically, by figuring out the amount of charge measured in coulombs. Coulombs is our unit of charge. The amount of charge in coulombs flowing past a particular point in the wire every single second. How many coulombs, how much charge is moving past a particular point every second? Every second. Here's what this looks like. So here's our formula. This is the first tool we're going to use today. It's I, which is current, is equal to Q, which is the amount of charge in coulombs, divided by T. And I know what you're thinking. Why don't we use C for current and then use, I guess, well, then you'd still have a thing. We want to use C for charge. But C means something very specific, right? We've seen C before, and what does it mean? Speed of light, right? C is already something very specific in physics, and so we want to leave C alone. And we've used Q before, and this is what's a little bit interesting. We've used Q to represent what? Heat, right? A specific type of energy. Here we're still using Q to represent a specific type of energy, but here we're using it to represent charge, electrical potential energy. It's a little bit different. I don't know why we can reuse Q, but we don't want to reuse C. I don't make these variables up. I just use them. And so current is equal to Q divided by T, which is the amount of charge passing a particular point every second. And the units for current are amps or amperes with a capital A, ampere, and it's basically equal to 1 coulomb per second. 1 coulomb per second equals 1 ampere. Okay? We okay with that so far? That's one way to quantify current. Can you think of another way we can quantify current? So using our analogy of a garden hose, this would be the equivalent to saying, what is the volume of water that passes a particular point every second? Okay. That would be basically the equivalent of this, the amount of charge passing every second. Can we think of another way we could do it with our garden hose? What about the number of water molecules that pass a particular point every second? Right? And you might think, wow, what's the value in that? And the only answer I would have for you is that the number of water molecules dictates how it's going to behave thermodynamically. Right? So we could also measure current in the amount of electrons flowing through the wire. And in order to do this, we need our second tool, which is that the charge of an electron is equal to, and this is just the magnitude of the charge. It's not the direction, because the electrons are negatively charged, right? But the magnitude is 1.6 times 10 to the minus 19 coulombs. And so the reason I didn't include the negative there is because we're talking about the magnitude and not necessarily the direction or the particular flavor of it at this point. All right? So that's our second tool that we're going to introduce. So far we've talked about current in terms of charge per time, charge per unit time, and then the charge of a single electron, 1.6 times 10 to the minus 19 coulombs. 1 times 10 to the minus 19, is that a big number or a small number? It's a small number. That's a really, really small number. Okay? So you need an enormous number of electrons moving to get basically 1 amp, which is 1 coulomb per second. Now you start to think about, why does this even matter? Because if you've got a wire carrying a 1 amp or 2 amp current, that's an enormous number of electrons that you can insert into your body should you be so unfortunate as to become a ground for those moving electrons. Make sense? Okay, cool. All right, so here's a visual representation of that. And again, this is dealing with using the analogy of water moving through a hose. And so here we have 4 electrons moving through, and so we can count it as the number of electrons that are moving through that point at any given time, or we can deal with it as the total amount of charge moving past a particular point at any given time. And it's really a question of, what do you want? Do you want to know the number of electrons, or do you want to know the amount of charge? Right? Do you want to know the volume of water moving through your hose, or do you want to know the number of water molecules moving through the hose? Anyone think that the number of electrons seems a little excessive? I do, right? Charge, I'm like, okay, we can handle that. The number of electrons, that's just an astronomically large number of electrons. But meaningful when you think about, the reactions and how they involve electrons. All right. Any questions about that question? All right. Our next one. What is voltage? What is voltage? This is a good one. What is voltage? So specifically in physics, voltage is the potential difference across a circuit. The potential difference. And this is the electrical potential difference. So we're dealing with like electrical potential here, having to do with relative amount of charge on either side of the circuit. But this is set up by an energy source, right? So you have a battery that has a positive terminal and a negative terminal, right? Y'all seen a battery? Think of like a AA or a AAA battery that has the little, what's the type? Eversion on one end. That's usually the positive terminal, and then the negative terminal is on the other end. And so the negative terminal is negative because it's a source of electrons. And then once you put that battery into your circuit, you have a source of electrons, and you have a positive terminal. And what do you know about electrons? How are they charged? Positively or negatively? Negatively. And what are negatively charged particles attracted to? Positive. So they want to move from the negative terminal to the positive terminal. Negative terminal is your source of electrons. Positive terminal is where those electrons want to go. This is why one of the reasons batteries don't last forever, because you lose your source of electrons and they all go over to the positive terminal. Now you can recharge it and reset up that charge, and that's what car batteries do. Is as you're running your car, it resets up and reestablishes your terminals, or what we call nodes, the cathode and the anode. Okay, but eventually even that's not perfect, right? Because you can't get all of that charge back. You lose some every time, and car batteries don't last forever either. The fact that you can make a car battery last for 5 years or longer, that's a miracle. It's a miracle. It's not really a miracle, but it requires an incredible amount of work. All right. In our houses, we're usually dealing with potential of somewhere between 110 and 120 volts. So when any particular power source in your house, you're usually dealing with that amount of potential difference. And that's something that's important to keep in mind. Now, some of the bigger appliances, it's not a big enough potential difference, and you need more encouragement of electricity to move because you have a greater demand. So you need like maybe a 220 line to run like a major electrical appliance, like an electric dryer or a hot tub. Right? Not like a blender. Blenders can run on 110 or 120, unless you're running a blender and a food processor and a hair dryer and something else all at the same time. You ever try to do that, and then your house just freaks out and it just shuts everything down? You got to go over to your circuit and flip switches back on. Anyways, sorry. Another story for another time. All right. So voltage is directly related to current, right? I mean, it's cool to think of what voltage is, that it's a potential difference across a circuit, set up by having a positive node and a negative node. Well, that's cool. But voltage is related to current. The more current you have, the more voltage you have. That's what we mean by directly related. Okay? The more current you have, the more voltage you have. And the more voltage you have, the more current you have, as long as something else remains constant. Okay? And so here's this formula. Here's our third tool. That voltage is equal to current times resistance. V is voltage, I is current, and R is resistance, measured in ohms. And unfortunately, we're not going to get a lot of time to talk about resistance. It's just the nature of, like, we need to talk about magnetism. We'll talk about resistance a little bit with our discussion of magnetism. But yeah, we'll only really talk about resistance in as much as we can to relate it to voltage and current. Okay, resistance measured in ohms. So what is voltage? Voltage is the potential difference, and it's a value that's directly related to current. So as current, if your resistance remains constant, so your resistance doesn't change from one situation to the other, if you increase your current, you're going to increase your voltage, right? And if you decrease your current, you're going to decrease your voltage. How do we know that? Well, let's assume for a minute that our current is 1 amp, okay? That our current is 1 amp, and that our resistance is 1 ohm, okay? 1 amp, 1 ohm. What's 1 times 1? 1, okay? So then our voltage is 1 amps times ohms, and relating that back to volts, which is what we measure voltage in, is a little bit complicated. You can't do it directly, so we'll just leave it as 1 amp times ohm. All right? Well, now let's leave our resistance the same, still 1 ohm, but let's double our current. So now we have 2 amps instead of 1 amp. What's 2 times 1? 2. And now our voltage has doubled from 1 amp ohm to 2 amp ohms. Okay? Sound all right? You want to do some problems? Maybe. Yeah, it's at the end of March. March has been a very busy month for me. I don't know if I'm ready for it, but I'll do it if you want me to. It's okay. It's okay if you're there. All right. So the first question we're going to deal with is this one. How much current passes through a circuit if 65.2 coulombs of charge passes by a point each minute? How much current passes through a circuit if 65.2 coulombs of charge passes by a point every minute? All right. So what are we given by this problem? And I know I've already mapped this out. I had some time, mapped this out already. If that bothers you, I'm sorry. I don't know if you prefer solving it on the board together or already seeing it played out. So this problem gives us our amount of charge, right? It tells us 65.2 coulombs of charge pass a point every minute. Okay, so we know Q, and then look at what I did with T. I said that T is 60 seconds. Why did I give it in seconds and not in minutes?
Our units are in seconds.
Yeah, our units that we have for current are amperes, right? And amperes is coulombs per second and not coulombs per minute. So the problem gave us that it happens every minute. We know that a minute is 60 seconds, right? Right? We know a minute is 60 seconds. And so we'll replace 1 minute with 60 seconds. That way we know our units will be proper. Okay. Our tools, the only tool that we need for this one is current, which is I is equal to Q divided by T is equal to charge divided by unit time. What do we want? We want current. Well, that's wonderful because our tool is already in that form. Current is equal to charge divided by time. We'll plug in our charge, 65.2 coulombs. We'll plug in our time, 60 seconds. and I know that's ugly, but you can see it's 1.09. 1.09 amps, because we know a coulomb per second is equal to an amp. Okay, so this wire is carrying a current of 1.09 amps. 1.09 amps. Which means there are a whole bunch of electrons passing that point every second. Right? If you don't believe that, we'll do a problem in a minute, and you'll see that. All right? Are there any questions about this one? We okay so far? And electricity is somewhat similar to some of the other concepts that we've had where it's not super easy to figure out exactly what's going on, but the algebra's simple. And sometimes that's better. You know, the algebra I can do. If you ask me to really explain what's going on, I can attempt at it, but I don't know if I'm going to get it exactly right. It's okay. Unless, of course, you decide to become an electrician, then you better figure it out. There's a reason why electricians make a lot of money. It's because it's very, very dangerous. That's one of the reasons. Plus, there are very few people that are, skilled in that trade. All right, so the next one. How much charge passes a point each hour if the current is 2 amps? If the current is 2 amps. How much charge passes a point each hour if the current is 2 amps? All right, so for this one, we go through and we do the same thing. What do we have? What are we given? What does this problem give us? Well, it gives us the current, right? It gives us our current, which is I, and it tells us that our current is equal to 2 amps. 2.00 amps. You agree with that so far? We're on the same page? All right. And then tools. We have our tool that says current, I, is equal to Q divided by T. And we want Q, right? So we need to rearrange our tool to solve for Q. And the way we do that is we get Q by itself. Right now, T is being divided away from Q. How do you get rid of something that's being divided away? You multiply it. So we'll multiply both sides by T. These T's cancel out. This T, look at that, showed up over here. So it looks a little bit chaotic. Sorry for that. But hopefully it's all good now, right? We're walking through it together. It's peaceful, calming. Maybe not peaceful and calming, but it's okay. If it's not, let me know. All right, so these T's cancel out, and we get that Q is equal to I times T. Well, now we'll plug in our current, which is 2.00 amps, and we'll plug in our T. Oh, no, I cut off the edge of it, which is 3,600 seconds. Why did I put an hour into seconds? What is the unit amp equivalent to? Coulombs per second, not coulombs per hour, right? So I gave us that the time that it gives us is 3,600 seconds. Do you agree that there are 3,600 seconds in an hour? I don't know if you've ever thought about it before, but there are 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. Okay? So we'll multiply our current, which is 2.00 amps, coulombs per second, times 3,600 seconds. Seconds cancel, leaving us with just coulombs, and that's good. Why? What is the problem asking us for? It's asking us for charge, which we measure in coulombs. So algebraically, we know we're on the right track, and then it's just a matter of getting the math to work. And 2 times 3,600 is 7,200 coulombs. So how much charge passes a point each hour if the current is 2.00 amps? Now, why are we representing this number with 2 significant figures? And the answer to that is there's really not a good reason. Because if it's telling us each hour, we can assume that that's exactly 1 hour, right? And an hour is exactly 3,600 seconds, meaning that should not limit our number of significant figures. And instead, we should present our number with 3 significant figures, because 2.00 has 3 significant figures. But in order to do that, I would have had to write this in scientific notation. And I'd have to write it as 7.20 times 10 to the third power. I don't want to do that. So I sacrificed a significant figure to give you something that's easier to digest. You're welcome for that. Okay, sometimes sacrificing a significant figure is worth it. Right? It's like when you, do any of you drive? Okay, but even if you don't, you will at some point. It's sacrificing your right of way to avoid a collision, right? Okay, sorry. All right. Wow, this one just looks. Wow, this one looks ugly. Gosh, we'll walk through the mess, and we'll find a nice clear path through it. So, how many electrons pass a point each second if the current is 3.00 amps? How many electrons pass through a point each second if the current is 3.00 amps? All right, so what are we given? And for this one, I sacrificed, really what happened is I wrote out have, tools, and want, but then I needed to write the answer. So I sacrificed those for the answer. This one, I don't know if it was a great sacrifice. We'll figure that out in a minute. So what do we have? This should say have right here. And you can see the semicolon is still there, right? It hung around. So what do we have? Well, it tells us each second. So time is 1 second, right? And that's wonderful. Whenever one of your givens is 1, you love that. Because 1 times anything is what? 1, right? And anything divided by 1 is what? Itself, right? So you love 1, right? You love 1. I love 1. You love 1. But then you're like, no, I don't really love 1 because if I only have 1 cheeseburger, that's sad because it's not going to fill me up. I love 2, right? Or 3 or 4. I'm sorry. What else do we have? We have current. I is equal to 3.00 amps. So those are things that are given to us by the problem. Now it should say have and then a colon, but the have was sacrificed. Okay, the colon's still there though. So is the colon from tools. You see that? It hung around too. It made it. It wasn't sacrificed. But then the tools that we have current is equal to charge divided by time, and that's good, right? We're getting in the right direction because we're figuring out an amount of something that passes by every point. But that's not the only tool we need. We also need to know what is the charge of an electron. And this is where we have our 1.6 times 10 to the negative 19. Okay, so that's in there as well. That's another tool. And this one, I made a mistake. There wasn't enough space, so I brought it down here. Okay, so those are our tools. Those are what we have. Now, what do we want? And this should say, what do we want here? But that got sacrificed, as did the colon. Okay? We want the number of electrons, right? But first, in order to figure that out, we can't just go straight to the number of electrons. First, we have to figure out the amount of charge that passes through a point at any given second. So we rearrange our tool to solve for Q. Right now, T is divided away from Q. How do we fix that? We have T divided away. We don't want anything divided away. We want Q by itself. Let's multiply T, right? We'll multiply T to both sides. These T's will cancel. We'll get Q is equal to I times T. We've seen that tool before. In fact, we used it in our second problem. Okay, so we'll do our our current, which is 3, oh gosh, that got sacrificed as well. 3.00, gosh, a lot of things got sacrificed in order to present this answer. This one was not worth the sacrifice. Right here, there should be a 3 and a 0 there. The point made it through, but the 3 and the 0 did not. Okay, so 3.00 coulombs per second, which is the same thing as 3.00 amps, right? Do you agree? That's something that we were given, times our amount of time of 1 second. 3.00 times 1 is what? 3.00, right? What's 5,000 times 1? 5,000. What's 10,000 times 1? It's 10,000, right? What's 10,000 to the first power? 10,000. What's 10,000 to the 0th power? 1. Why is that? Anyways, so our Q, or the amount of charge that passes a point every second, is 3.00 coulombs. Are we done? Nope, the problem wants to know how many electrons. So we've got to do one more step. The number of electrons is equal to the total number of charge divided by the charge of each electron. And the way we know that that's the way we do it is the same way you would say, let's say, let's say you had a fundraiser. Any of you ever been part of a fundraiser before? Have any of you never been part of a fundraiser? Okay, everybody, we're on the same page. Let's say your group has to raise $5,000, okay? And there are 10 people in your group. How much does each person need to raise? So you got to raise $5,000, and there are 10 people in your group. How much does each person need to raise?
500.
How do you know?
Divided.
Yeah, you do the total divided by the number of parts, right? We're going to do the same thing here. We're going to do our total charge divided by the charge in each parts. Okay, but in this case, we're trying to figure out the number of parts. All right, so we've got 3.00 coulombs divided by the charge of a single electron, which is 1.6 times 10 to the minus 19 coulombs. Coulombs cancel, and we're left with 3.00 divided by 1.6 times 10 to the minus 19. It's a really small number, right? So if you divide a reasonable number, 3, by a really, really small number, what should you get? A big number or a small number? You should get a big number, right? If you divide a reasonable number by a really, really small number, you should get a big number. And so we get over here, and we find out that the number of electrons passing through a point in this wire every second is 1.88 times 10 to the 19 electrons. A 188 with 17 zeros afterwards. It's a lot of electrons. Would you agree? That is a lot of zeros. That's a big number. That's the kind of number that would blow the mind of a child. It kind of blows my mind too. But to think about that electrons are so small, you can have that number of electrons. And this is a wire that's carrying a current of 3 amps. That's pretty high. That's a pretty large current. There are very few things that you would do today that would involve that amount of current. Who knows what 5 or 10 years from now would look like. But playing around with that amount of current is potentially very dangerous. Yeah, potentially very dangerous. Because it's just a large number of electrons to enter into your body if you, for some reason, become the electron receiver. All right? Sorry about all the moving and shaking and all of that. Man, I sacrifice. I don't see what happens is when you go on a race, if you touch anything that was a single, what's the term I'm looking for? A single pass to right, it erases the whole thing. So it didn't just erase a piece of my 3, it erased the whole thing. And I don't know why I didn't see that. I'll add that 3 back in before I send these slides out. But were you able to follow okay through the messy path? It's like holding somebody's hand through pitch blackness, right? You don't know where you're going, and you get to the end, you have no idea what happened, but you got to the end, you're alive, right? Yay! You ever feel that way after some time spent with me? Like, I have no idea where we went, no idea how I got here, but I'm alive. Time to celebrate. That's the way my kids feel with me after every day. It's every day. Although I don't think they think that deeply yet. They're little. All right. We got a couple more questions to do together. You okay? The rest of them are going to deal with voltage. Did you have a question, Micah? Okay. So how much current is in a wire with a 12-volt power source and 5.05 ohms of resistance. A 12 volt power source and 5.05 ohms of resistance. 12 volt power source, it's like a car battery, a battery on a drill. All right, so what do we have? What are we given? We know that our voltage, right? What's the voltage of our power source? 12 volts, right? And we know our resistance. What's our resistance?
5.05
Ohms. And the ohm got cut off there. You'll see it in your version of the slides. This TV's cutting off the edge of my slide. I mean, granted, that ohm it's packed in there. Like it barely fits on here. So I'm not surprised it cut it off, but a little disappointed nonetheless. So I'm the youth director at my church, and I had to step outside to let somebody into the church. And when I got back in, all of my junior hires were standing on the tables. I wasn't surprised by it, but I was still a little disappointed, if that makes sense, right? My kids were playing with Play-Doh the other day. I stepped away for a second, and they started eating it. I'm not surprised by it. A little disappointed. All right. Wow. There, he just ran you down like a rabbit trail. You're welcome for that. Just put you right on my back and took you through a day in the life of myself. All right, so tools. Well, we have this tool that says our voltage is equal to our current times our resistance. V equals IR. V equals I times R. Right? That was a tool we saw on our second slide. What do we want? We want the current. Wow, why does this N have such a tall... Wow. Gosh, that is terrible. That's probably the worst thing that I've shown you today. I apologize for that. I was actually going to make this announcement when I first started class. I can't even tell you the number of mistakes I've made today. Zion asked me how I was doing because he was the only one here when I walked in. And I'm doing fine. Just for some reason, I've made countless mistakes today in all sorts of different avenues. I don't know what's happening. I slept okay last night. I mean, I just don't know. Maybe it's like I'm finally, my body is finally catching up with my age, right? So my brain isn't working as well as it used to. And I'm not prepared and ready for it. Anyways, so we want our current. Right now, our tool is not set up to solve for current because right now we have our resistance multiplied to our current. We want current by itself. How do we get rid of that resistance? Divide it away from both sides. So that's what's going on here. We divide resistance from both sides. This cancels out. We divide resistance over here. And now we have a tool that says current is equal to voltage divided by resistance. Do we know voltage? We do. Do we know resistance? We do. And so we'll go ahead and plug that in. Our voltage is 12 volts. Our resistance is 5.05 ohms. And we'll leave just our units like this, volts divided by ohms, because it's not a real clean transition from that to amps. Okay, but we can leave our units like this, 2.4 volts divided by ohms. Okay? Any questions on this one? Straightforward enough? Okay. What does that actually mean in terms of current? We don't exactly know because it's not given to us in coulombs per second. But algebraically, it's not entirely impossible to do. All right, so the last question we're going to do together. What power source is necessary to power an item that requires 2.00 amps with 110.0 ohms of resistance? Okay, so 2.00 amps with 110.0 ohms of resistance. So what do we have? Well, we're given our current. And we're also given our resistance, right? That's good. It looks like we're moving towards using this tool here, that our voltage, that our electric potential is equal to current times resistance. And then what is the problem actually asking us for? What's the power source, right? What potential difference is necessary? What voltage do we need? Well, that's wonderful because our tool's already in the right form to do that, right? Do we know current? We do. Do we know resistance? We do. And so we'll plug in our current of 2.00 amps. We'll plug in our resistance of 110.0 ohms. And we'll get that our voltage is equal to 220 amps ohms. And again, we won't convert that over to volts because it's not exactly a nice clean transition. But we have an assessment of the amount of electric potential necessary. Power is a little bit cleaner of a tool to use, but anyways, this is called Ohm's law. That voltage is equal to current times resistance. All right? Any questions or thoughts or concerns? Okay, so just a reminder, if you haven't pulled out your materials to turn in today, that we are collecting lessons 13, 14, 15, quiz 5, exam 5, lab 5. Anything that you haven't turned in previously, so for some of you, you're missing some assignments, and then whatever you have to turn in, I will gladly take. All right, we are